Hello, this is chapter number 7 from the textbook of Mechanics of Materials by Mohr and Johnston. The title of the chapter is Transformations of Stress and Strain. Before this, we have studied the basic stresses and strains, normal stresses, normal strains, and axial loading, torsion, bending from chapter number 1 to chapter number 6. Now the transformation of stresses is a topic to study to know how the stresses can transform from one coordinate axis to the other coordinate axis. If we rotate our coordinate system, or if we want to find stresses at any other plane which is not in our given coordinate system, not in the direction of our coordinate axes, horizontal and vertical axes. So how can we find stresses at any other plane, or where the stresses will be maximum? For example, we have a two-dimensional state of stress, sigma x, sigma y, and tau xy. So we know the sigma x, sigma y, and tau xy values, but what will be the value of sigma and tau at this plane? Similarly, where will be the sigma maximum and where will be tau maximum? So we can find these values in this chapter by using the transformation formulas. Before that, I want to discuss a few basic things. Sigma will be positive if the stress is tensile, both sigma x and sigma y. And how can we define tau is positive or negative, tau xy? So in this case, either this tau xy is positive or negative. We need to know this. We will apply this in our chapter. So tau has basically two subscripts, x and y. X denotes the plane perpendicular to the axis perpendicular to the plane of stress, and y denotes direction of the force or stress. So here, the axis perpendicular to the plane of stress is x-axis, positive x-axis, and the force itself is in positive y-axis. Both x and y are positive. Both have same sign actually. So tau xy is positive. Let us see here. If this is positive, it means all of these taus are positive. Here let us see. This plane is perpendicular to negative x-axis, and the force is in negative y direction. So negative x and negative y, both signs are same. So this tau xy is positive. Here plane is positive y-axis and the force is in positive x-axis. Both are positive, same sign x and y. So tau is positive. But if we see here, like this one, now the plane to this stress is positive positive x-axis, this is positive x direction, and the force is in negative y direction, downward. So positive, negative, opposite signs. So this tau xy is actually negative. The value is negative, direction is negative actually. Here we can see plane is positive y plane, the force is in negative x-axis, positive, negative, both subscripts are opposite, so it is negative tau xy. Similarly here, the plane is negative x-axis, the force is in positive y-axis. Negative and positive, opposite signs. So subscripts have opposite sign, so the tau xy is negative. So we will use the positive or negative values of tau xy using this convention, using this definition. And you already know sigma x and sigma y will be positive if they are tensile, they will be negative if they are compressive. This sigma x is positive, sigma y, if it is compressive, it is negative. Okay, so let us move forward. Okay, tau xy, if it is positive here, all of them are, sorry, if it is negative here, all of them are negative, remember it. If it is positive here, all of these four are positive. They are positive, they have same magnitude. Okay, so now we will discuss how we can find maximum stress, at which plane stress will be maximum, or if we are given theta angle at that specific plane, what will be the value of sigma x, sigma y and tau xy. So in the transformed coordinate system we will find stresses and strains. Okay, let us move. Before that, we must know that in the general state of stress in a three-dimensional space in x, y, z planes, we have 6 components of stresses, 3 normal stresses and 3 shearing stresses. 3 normal stresses are perpendicular to the 3 normal planes. This sigma x is perpendicular to the x plane or yz plane in the x direction. Sigma y is in the direction of y. Sigma z is in the direction of z. Now, shearing stress. There are 2 shearing stress on x and the yz plane. Sorry, on the x. Sorry, in the yz plane. Yes, is yz plane. What are those 2 shearing stresses? Tau xy and tau xz. The first subscript x denotes perpendicular direction to the plane, x direction, and the second subscript y denotes direction of the force. Here the first subscript x denotes perpendicular direction of the plane, perpendicular axis to the plane, and z denotes direction of the force. Okay, similarly on each surface there are 2 shearing stresses. Here are 2 tau xy, tau xz, tau yx, tau yz, tau zx, tau zy. Okay, 3 normal stresses and 6 shearing stresses, but among these 6 shearing stresses, each corresponding to components are same. For example, tau xy and tau yx are same, so we can count them single component. Similarly, tau xz and tau zx are same. Similarly, tau zy and tau yz are same. So each 2 shearing stress components are same. So we may say that we have 3 shearing stresses: tau xy, tau yx and tau zx, because tau xy is equal to tau yzx, tau yz is equal to tau zy, and tau xz is equal to tau zx. We can write them in form of stress tensor, famous stress tensor, where the diagonal components are denoted by normal stresses and non-diagonal components are denoted by shearing stresses. You know this stress tensor very well. So the diagonal components are normal stresses. Here the corresponding members, for example tau xy and tau yx, their shearing stresses equal to each other. Tau xz and tau zx are same. Tau yz and tau zy are same. So this is a symmetric matrix, actually 3 by 3 symmetric matrix. Okay. Same state of stress is represented by different set of components if xz's are rotated. So if these axes x, y, z axes are rotated to x dash, y dash and z dash directions, so this stress element is rotated, and we have another 6 components of stresses: sigma x dash, sigma y dash, sigma z dash, tau x dash y dash, tau y dash x dash, and tau x dash z dash. Again, a similar kind of stress tensor is obtained with 9 components. Among those 9 components, 6 shear components are, there are 6 shear components, and every two corresponding shear components are same, so we can call them similar, and we have only 6 stress components. If we find these 6 stress components, 3 normal and 3 shear components, we can find this whole stress tensor. So okay, in the first part of this lecture, we will find the components of stresses, how the stresses are transformed under rotation of coordinate axis. And in the second part of the lecture, we will study the stress conditions necessary to cause failure. So we will discuss some failure theories. Let us move towards the first part of the chapter. The first very basic term we will use throughout this chapter is plane stress. What is plane stress? If there are two, for example, in this cubic element actually has 6 faces. 3 faces are visible to us and 3 are hidden. Among these, every 2 faces are perpendicular to some axis. For example, 2 faces are perpendicular to x-axis, 2 are perpendicular to y, and 2 are perpendicular to z-axis. So plane stress is a state of stress in which 2 faces of the cubic element are free of stress. 2 faces are free of stress, but those 2 faces must be parallel. For example, here this face and the back face are free of stress. So only 4 faces are experiencing stresses. If I draw a 2-dimensional element out of this, these 4 faces, sigma x, sigma y, and tau xy, there are stresses on these 4 faces, and the other 2 faces, the face which lies in this plane of presentation, plane of this your screen, it is free of stress. So 2 of the faces which are parallel to each other, they are free of stress. So we have only 2-dimensional state of stress, where sigma x, sigma y, and tau xy exist, but sigma y, tau xz, and tau yz are 0. So any stresses in any one of the direction are 0. In this case, we are calling it z direction. All components of stresses involving z direction are 0, either shear stresses or normal stresses. But there are stresses in x and y direction. Okay. The state of plane stress occurs in a thin plate subjected to forces acting in the midplane of the plate. Here's an example. Here's a thin plate, and these forces are acting at the mid of every plane, midplane. This is mid of the plane. Mid means there is no effect of rotation. This is also mid of the plane. So this thin plate has no stresses in the thickness direction, and this is under a state of plane stress. Similarly, state of plane stress also occurs on free surfaces of a structural element or machine component that is at any point of the surface not subjected to an external force. So this surface of this shaft is not subjected to any force. So there is no stress in this direction or in this surface. So the free surfaces are also under plane stress condition. Okay, let us move forward. Transformation of plane stress. So now we are going to find the stress components in transformed coordinate system. If we have a three-dimensional, if we have a cube, for example this one, and we cut it into a wedge element like this, there are x and y directions. Initially we are just finding transformation in two-dimensional now, two-dimensional plane. In two dimensions we have x and y. X is horizontal and y is vertical. Okay, if once we have cut the element and we have a wedge element, here is a surface. This surface, it has to this surface is perpendicular to an axis, which is x dash axis, and a parallel axis is y dash axis. So in order to find normal and shearing stresses in x dash and y dash directions, we have to apply equations of equilibrium. This x-axis is rotated by angle theta. Similarly, y is also rotated by angle theta. Okay. Initially we had sigma x, sigma y, and tau xy. These stresses, let us convert these stresses into forces first. In order to apply equations of equilibrium, we have to convert stresses into forces. So the stress can be converted into force if we multiply it with area. So this area, let us consider this area is delta A. So, and this angle is theta. So this area will be delta A sine theta, and this area is delta A cosine of theta. So all stresses acting on this area have been multiplied with delta A sine theta, and stresses on the vertical surface are multiplied with delta A cos theta. Now we have to resolve these forces into components. Okay, the stress perpendicular to this surface in x dash direction is sigma x dash, and by multiplying it with this area delta A, so delta x sigma x dash into delta A. Similarly, the stress parallel to this area is tau x dash y dash, and multiplying it with delta A, so it is converted into force. So let us resolve all these stress components into let us apply equations of equilibrium to all these force components. I have converted all stresses into forces now. So let me apply equations of equilibrium. Okay, I will use a different color of ink for this. Let me use blue color. This component of stress can be resolved into two components. Which one? This is angle theta, because this is vertical force and it is making an angle theta with y dash. Vertical is making angle theta with y dash plane. Horizontal force will make horizontal forces will make an angle of theta with x dash plane. Remember that horizontal line is making angle theta with x dash, and vertical lines are making angle theta with y dash. So this is vertical force, it will make angle theta with y dash direction. Okay, then this force can be converted into two components. Let me do them one by one. Okay, this force is converted into two components. Summation of forces in x dash direction are equal to 0. One of the force in x dash direction is sigma x dash delta A. component of this force in x dash direction is this one, and it is equal to sigma y dash delta a sine theta. This was the force, and again sine theta for this component, because theta is with this with y direction, with y dash direction, so it is x dash component, so it is sine theta. Okay, so this component is here. Now let us resolve. I will do them one by one because there is no space to do it. Okay, I will resolve it here. This and this horizontal force will make angle theta with x dash direction. So this force is tau xy delta a sine theta. Already this is force into, because angle is made with this side, it is cosine theta again. This force is here. The negative sign means it is opposite to x dash direction. Here is x dash direction, it is opposite to x dash direction, so negative sign. Okay, let us resolve another force. I will delete this one, and let me resolve another force. This force so this is our theta, and this component sigma x delta a cosine of theta. This is already our force, so the component is making an angle theta. Theta is with this side, so again cosine of theta. So here is it. Negative sign means it is opposite to the x dash direction. Similarly, you can resolve this force and you will find this component. You can do it by yourself by summing all these components. I will remove signs. By summing all these components, you can have this equation of equilibrium. Okay. Similarly, by resolving all these forces into the y dash components and adding all the components, you can write this expression. You have learned this technique in engineering statics. Okay. By rearranging, we can rearrange these expressions. Let me rearrange this expression number 1, which contains components in x dash direction. By rearranging this expression, I can write sigma x dash is equal to sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 cosine 2 theta plus tau xy sine 2 theta. The simplification steps are available in the textbook, and you can do it. You can see from the textbook. Okay, this is sigma x dash. If I want to find sigma y dash, I have to there's an angle of there's a difference of 90 degree between x dash direction and y dash direction. So if I replace theta with theta plus 90 degree in this expression, Let us replace theta with theta plus 90 degree. You can do this implication by yourself. We can find sigma y dash, which will be sigma x plus sigma y divided by 2 minus sigma x minus sigma y divided by 2 cosine of 2 theta minus tau xy sine of 2 theta. Okay. Now if we simplify this expression, we can find tau x dash y dash is minus sigma x minus sigma y divided by 2 sine of 2 theta plus tau xy cosine of 2 theta. So we have transformed sigma x, sigma y and tau xy into sigma x dash, sigma y dash and tau x dash y dash. But for all of them, what we need the values of sigma x, sigma y, tau xy and theta. If we know them, if we know sigma x, sigma y, tau xy and theta, we can find these. So if we are given a matrix sigma x, sigma y, tau xy and a value of theta, so we can find sigma x dash, sigma y dash, tau x dash y dash and tau y dash x dash. Okay, using these equations of transformation of stresses. Okay, this is in plane stress. We have only two-dimensional state of stress. Okay, we can further play with these expressions to find other component, to find some other important stresses. What can we do? We can find principal stresses from these expressions. What are the principal stresses? We will discuss it now. Okay. How can we do it? Let me remove, make some space. Okay. This expression, this term sigma x plus sigma y divided by 2, it is actually average stress. So I can write this expression again. Sigma x dash minus sigma average is equal to sigma x minus sigma y divided by 2 cosine of 2 theta plus tau xy sine of 2 theta. Okay, again this expression can be written as it is. Tau x dash y dash sigma x minus sigma y divided by 2 sine of 2 theta plus tau xy cosine of 2 theta. I am just squaring both sides of these expressions and adding them. Let me add them. So this will be sigma x dash minus sigma average square plus tau x dash y dash square is equal to sum of these two terms. Let me call sum of these two terms equal to r square. So what will be the r actually? R square, it is equal to sigma x minus sigma y divided by 2 square plus tau xy. You can do this simplification, you will find this r square equal to, you can add these two terms, these two sides, and it will be equal to r square. I am calling this term equal to r square. So this expression, what is this expression? This is expression of circle. Expression of circle is usually x square plus y square is equal to r square. X and y are two directions, two coordinate axes, two coordinate positions, and r is radius of the circle. So here we have two directions, sigma x dash, tau x dash y dash, r is radius of the circle, but here we have sigma x dash minus sigma average. In this expression we have center of the circle at 0, 0. This expression can be rewritten actually as x minus 0 square, so y minus 0 square is equal to r square. So center is at 0, 0. But in our case we have an expression of this form, sigma x dash minus sigma average square plus tau x dash y dash square is equal to r square. So if we draw two axes, sigma x dash and tau x dash y dash axes, so our center lies at sigma average and 0. Let me rewrite it here. It is actually so our center lies at sigma average and 0. So the center C, it is actually sigma average and 0. R square, R is actually radius of the circle, this circle. This is actually our Mohr circle. How we can draw this circle, we will study it in the following slides. In this circle, the horizontal axis shows actually normal stress, sigma x dash, and the vertical axis is for the shear stress. So all the points on horizontal axis are showing normal stresses. There is no shear stress on horizontal axis. All the points on vertical axis are showing shear stresses. There is 0 normal stress on the vertical axis. So here on horizontal plane we have 2 points A and B. Okay, for this circle let me first tell you that sigma average, we have defined it earlier, sigma x plus sigma y by 2, and R is sigma x minus sigma y divided by 2 square plus tau xy square. Okay, these 2 points A and B, they are denoting the maximum and minimum normal stresses. There is no stress more than at point A. There is no stress more than sigma A, and there is no stress lesser than sigma B on this circle. Okay, so sigma A is maximum normal stress, sigma B is minimum normal stress. But remember that at both these points shear stress is 0. So the value of normal stress where shear stress is 0 is called principal stress. So sigma A and sigma B are our principal stresses. Sigma A is maximum principal stress and sigma B is minimum principal stress. What is sigma A or sigma maximum? It is equal to, let me write it, sigma A or sigma maximum is equal to OA, from A to point A, or we can further write it as OC plus CA. What is OC? OC is average, sigma average, and CA is radius. So it is sigma average plus radius. Sigma minimum is equal to OB, at point B sigma is minimum. It is equal to OC minus BC. OC is sigma average and BC is radius of the circle. So we can write it as sigma maximum and sigma minimum are equal to sigma average plus minus radius, or we can write it as sigma x plus sigma y divided by 2, it is sigma average, plus minus radius is sigma x minus sigma y divided by 2 square plus tau xy square. Similarly, we can also find principal plane. These are principal stresses, sigma maximum and sigma minimum. These are the two normal stresses where shear stress is 0 at point A and point B. They are lying at horizontal axis. The shear stress is 0. So these two normal stresses are principal stresses. This is definition of the principal stress. Principal stress is a normal stress where shear stress is 0. Okay. Theta P is principal direction. So in this expression here, this is expression of shear stress. So principal stress or principal direction, principal stress is a normal stress where shear stress is 0, when shear stress is 0, and principal direction is a direction in which shear stress is 0. So if I put shear stress equal to 0, tau x dash y dash equal to 0, left side of this equation is kept equal to 0, so we can find theta from this expression, and that theta can be found from this expression, tan 2 theta. I will call that theta equal to theta p because it is principal direction, will be 2 tau xy divided by sigma x minus sigma y. This expression is for principal direction or principal planes, theta p. It will give us two values of theta p. First value can be found from this expression. Second will be just at a difference of 90 degree. Sigma maximum and sigma minimum are at an angle of 90 degree with each other. So if the given plane is in if the given element is in x and y direction, x direction and y direction, so by rotating it at angle theta p, there will be sigma maximum, and then again there will be sigma minimum. Sigma maximum and sigma minimum are at an angle of 90 degree with each other. Here we can see the sigma maximum and sigma minimum are at an angle of 180 degree. But in Mohr circle, always remember all the angles are in terms of 2 theta p. So actually all the angles obtained from Mohr circle must be divided by 2 to find the real angle. Mohr circle has all angles in terms of 2 theta, double angle. So in order to find actual angle, we have to divide the angles of Mohr circle by 2, remember it. So 2 theta p is equal to 180 here. So 2 theta between two principal stresses is 180 degree. So actually the difference between two principal angles is 90 degree. You can see it here. Okay, again, if either this rotation should be clockwise or counterclockwise, we can use a sign convention. Here in this book we are using a sign convention of positive for counterclockwise direction and negative for clockwise direction. When you will draw the Mohr circle by yourself, you can see graphically if the angle is clockwise or counterclockwise, but while using formulas you can use this convention, positive for counterclockwise and negative for clockwise. Okay, now to find maximum shear stress, where the shear stress is maximum at this point. Shear stress is maximum at point D. There is no point beyond point D which can show maximum value in the vertical direction, so in the vertical axis. So in the vertical axis, D is the maximum point, so tau maximum is equal to length of line CD, which is radius of the circle, and we already know radius of the circle is sigma x minus sigma y divided by 2 square plus tau xy square. Similarly, direction of maximum shear stress can be found. Okay, before that, when principal stress is shear stress is maximum at this point, the normal stress here, it is equal to sigma average. Normal stress is equal to sigma average. When shear stress is maximum, the normal stress will be average. So by putting normal stress equal to sigma average here in this expression, put it equal to sigma average, sigma x plus sigma y divided by 2, we can find the value of theta, and the value of theta becomes 10 to theta s. S is for shear plane, shear direction, it will be minus sigma x minus sigma y divided by 2 tau xy. Again the same convention, counterclockwise positive, clockwise negative. Okay, this theta s, there will be two theta s, again two maximum shear stresses at point D and at point E. They are apart by an angle of 180 degree in the Mohr circle. So actually there is a difference of 90 degree between two shear planes. So the two shear planes are separated by 90 degree with each other, from each other. Theta s1 is equal to theta s2 plus 90 degree. Okay, and the theta is actually, if we see here, this is shear plane and this is principal plane. They are at an angle of 90 degree with each other in the Mohr circle. So actually they are at an angle of 45 degree with each other. The two theta difference between principal and shear planes is equal to 90 degree. So actual difference is 45 degree. Okay, and when the shear stress is maximum, as I discussed earlier, the normal stress is equal to average. Here we have seen a principal element drawn at a rotation of angle theta p from the x-axis, and we can see principal stress sigma maximum and sigma minimum. If the stresses are principal, if the normal stresses are principal stresses, so there is no shear stress around this element. But after rotating the element by angle theta s, we have shear stress equal to tau maximum. If tau is maximum, there will be normal stress equal to sigma dash. What is that sigma dash? Sigma dash is actually average. When shear stress is maximum, normal is average. Remember it. Okay. Let us solve a numerical problem on this topic, and you can clarify some of your concepts. Okay. For the state of plane stress shown, determine the principal planes in part A. Principal planes means theta p. The principal stresses means sigma maximum and sigma minimum. And the part C is the maximum shearing stress and the corresponding normal stress. Tau maximum and its corresponding normal stress, sigma dash. Theta p can be found from this expression already derived. We are being given sigma x, it is equal to 50 megapascals. Sigma y, it is equal to minus 10. It is compressive, so we will have a negative sign with it. And tau xy, as we can see here, if this is tau xy, one of them, I will consider this force for example. The perpendicular direction is positive x-axis, the force is in positive y direction. Both have same sign, so it is positive. One of them is positive, so all of them will be positive. Tau xy is positive 40 megapascal. So by putting sigma x, sigma y and tau xy in this expression, we can find theta p. Similarly, putting sigma x, sigma y and tau xy in this expression, we can find part B, sigma maximum and sigma minimum. By putting sigma x, sigma y and tau xy in this expression, we can find tau maximum in part C. And when tau is maximum, shear stress is maximum, normal stress will be average, corresponding normal stress, sigma dash. So let us put all the values. Putting sigma x, sigma y and tau xy in this expression, theta p has been found. It is 26.6 degree. If one of theta p is 26.6 degree, the next will be by adding 90 degree to it. So by adding 90 to 26.6, we can find then the next value will be 116.6 degree. The values of this is direction of principal stress, or principal plane, theta p. The values of principal stresses are sigma maximum and sigma minimum are it can be found using this expression. By putting sigma x and sigma y and tau xy in this expression, we can find sigma maximum and sigma minimum. Once we have found sigma maximum, sigma minimum and theta p, we have to draw this element. It is necessary, remember it. If you in your exam or in your quiz, if it is asked to find principal stresses and principal plane, after that you have to draw this element. So theta p is positive 26.6 degree. So in counterclockwise direction, we will draw an element, this element, and sigma maximum and sigma minimum are principal stresses, so it means they are normal stresses. Sigma maximum is 70 megapascal, sigma minimum is 30 megapascal. Some of the students usually have a query that either sigma maximum should be plotted here or here. So we can see it in, when you use Mohr circle, it is very easy to know, but in a formula it is again not a difficult one. This was our x direction, this was our y direction. So x is 50 megapascal, y is minus 10. This is a greater value. Maximum, sigma maximum is associated or will be near to sigma, will be near to the x direction. So maximum value 70 megapascal. It is after rotating x axis to the theta p direction or theta p1 direction. Okay, it is 26.6 degree. Again, by adding 90 to 26.6, it is 116, so it is minimum. You can see sigma y is minus 10, so by rotating y, we can find theta p2 and sigma minimum, and we can find sigma minimum in theta p2 direction, which is negative 30 megapascal compressive. Okay, to find tau maximum, again we have the expression. By putting sigma x, sigma y, tau xy, it is very easy to find tau maximum equal to 50 megapascal. Direction of tau maximum is theta s. Either you can use the expression of theta s, this expression, or you can use theta is equal to theta p plus 45 degree. So theta s is equal to theta p plus 45 or minus 45, both are fine. So theta p minus 45 and theta s is minus 18.4 degree, and again adding 90 degree to minus 18.4, it becomes 71.6. Two values of theta s. Minus means it is in counterclockwise direction, it is in clockwise direction. Here it is theta s. Theta s is in counterclockwise direction. We have drawn an element at an angle of minus 18.4 degree. The stresses parallel to this element are tau maximum, which is 50 megapascal. And when tau is maximum, corresponding normal stress will be sigma dash equal to sigma average. Average is sigma x plus sigma y by 2, which is 20 megapascal. So here 20 megapascal in all directions. If it is positive, it will be tensile. If it is negative, it will be compressive. So once you find sigma maximum and sigma minimum and theta p, you have to draw its element. Once you find tau maximum and theta s, you have to draw its element. Let us move to, this was example number 7.01. Let us move to another example. It is a sample problem 7.1. Very important problem to clear some of your concepts, and it also involves your previous concepts. A single horizontal force P of 150 pound magnitude is applied to end D of a lever ABD. At point D, force P equal to 150 pounds has been applied. Determine in part A the normal and shearing stresses on element at point H having sides parallel to x and y axis. At point H, we have an element parallel to x and y axis. So in xy plane, this point is actually in xy plane. We have to find normal and shearing stresses. Normal and shearing stresses at point H, sigma x, sigma y, and tau xy. You have to find at point H. And then the principal planes and principal stresses at point H. Principal plane is theta p, and principal stresses are sigma maximum and sigma minimum. At point H, remember all of these stresses are needed at point H. So first we have to find this effect of force P at point H. If we move this force P from D to H, what we have to do? We have to add a couple and a torque. This P is actually producing torque around y-axis. Torque. What will be that torque equal to? That torque will be equal to P into 18 inches. Okay. And then this force P is also at a distance of 10 inches from point H. It is bending this beam in the y direction. So there is a moment around x-axis. It is rotating around x-axis, and the bending is produced in y direction. Remember it. Sorry. So this moment is P into distance from H, 10 inches. Okay. Let us first find this torque and this moment. Force is 150 pounds. So torque is 150 into 18, 2.7 into 10 power 3 pounds inch, or 2.7 kilopounds inch. Moment is 150 into 10, so it's 1.5 into 10 power 3 pound inch, or 1.5 kilopounds inches. So we have found torque and moment. The torque is actually producing shear stresses, and the moment is producing normal stresses. In which direction the moment is producing normal stresses? We have to recall our concepts of bending. Most of the students get confused with it. If here is a beam under pure bending, and if it is x direction, the sigma here and here, sigma will be maximum, and at this point sigma will be 0. Sigma will be 0 at neutral axis, but it will be maximum at outer surfaces. So sigma maximum is equal to mc over I. and it is in the direction of the length x, because it increases or decreases the length of the beam. So bending stress is always in the direction of the length. Here we can see in this beam, direction of the length, it is point h, direction of the length is y direction, so this is sigma y. Okay, either it is maximum or minimum or zero. If the force is in this direction, P, so it is maximum at point H and minimum at this axis. This is neutral axis. If we were given this point or this point, so sigma is minimum here. Okay, so sigma is maximum at point H, sigma y, mc over I. M is 1.5 kilopound inches. C is radius of this bar. Radius of the bar is given. It is diameter is given 1.2 inches, so radius is 0.6 inches. I is pi by 4, radius power 4. Similarly, tau xy is equal to Tc over J. We have studied it in our chapter of torque, chapter number 3. Torque is 2.7 kilopounds inch. C is radius and J is pi by 2, radius power 4. There is no stress in x direction because there is no normal force in x direction. Similarly, there is no bending in x direction, so sigma x is 0, and there is no shear stress in x direction, so sigma x is 0. Shear stress is always in a plane, not in a single direction. Sigma x is 0. Sigma y has been found from this expression. Tau xy has been found from this expression. So we have found sigma x, tau xy, and sigma y. Sigma y is this one. This is sigma x. This is sigma y. This is tau xy. Okay. First part of the question was to find normal and shearing stresses, sigma x, sigma y, and tau xy. Second part, to find theta p and sigma maximum and sigma minimum. We can simply put these values in the expression of theta p. This expression, we can find theta p, which is minus 30.5 degree plus 90, so 59.5 degree. Sigma maximum and sigma minimum can be found using this expression. By putting values of sigma x, sigma y, and tau xy, we can find sigma maximum equal to 13.52 ksi and sigma minimum equal to minus 4.68 ksi. Okay, minus 30.5 degree means clockwise rotation. Sigma x was 0, sigma y was 8.84. So sigma minimum will be after rotating sigma x by an angle theta p. This is sigma minimum because sigma x is lesser than sigma y. Sigma maximum is after rotating y dash. This is sigma y maximum. When sigma is maximum or minimum, these are principal stresses, so there is no shear stress. Okay, so this has been drawn. If we were asked, we have not been asked, but if we were asked to find tau maximum and theta s, so we can find it using this expression. But they are not asked in this numerical problem. Our next topic is Mohr's circle for plane stress. Up till now we have calculated principal stresses, maximum shear stress, principal planes, shear plane, and stress normal and shearing stresses at any other angle using established formulas. We have derived formulas for principal stresses, maximum shear stress, and sigma x dash, tau x dash, y dash, sigma y dash at any angle theta. So now we can use a graphical method which is called Mohr's circle. For Mohr's circle, we must know the given sigma x, sigma y, tau xy. Once we know sigma x, sigma y, and tau xy, these must be given, remember it. We need to point 2 points to draw 2 points on a graph papers x and y. Remember, x has coordinates of sigma x and minus tau xy, while y has coordinates of sigma y and plus tau xy. Remember that in point x, tau xy has a negative sign, in point y, tau xy has a positive sign. You can exchange them, but here we are using this as per our convention because we are using positive sign for counterclockwise angles and negative sign for clockwise angles. If you will change these signs, you will have to change the signs of angles as well, angles directions sign as well. So throughout the lecture and throughout the chapter, I will use x as sigma x minus tau xy, y as sigma y plus tau xy. I will explain how to draw Mohr circle. To draw Mohr circle, you have to initially draw two axes. Horizontal axis is sigma and vertical axis is tau. Okay. On a graph paper, first you have to take scale. How many centimeters or how many millimeters are equal to how much megapascals. After that, sigma x, sigma y and tau xy are given. So we have to plot point x as sigma x minus tau xy and point y as sigma y plus tau xy. Once you denote these 2 points, first step is to identify x and y points. Okay. Second step is join x and y using line which intersects horizontal axis at center point C. If we join x and y using a line, it intersects the horizontal axis, which is center of the circle C. And remember that C must have coordinates of sigma average and 0. These are already discussed. Okay, now you have a center point and external points of the circle. You can draw using a geometry tool. This is our center, this is outer point of the circle, so simply draw a circle. Okay, if we have center and outer point, we can draw a circle. So do remember that if you have an element with x and you have an element in xy direction, sigma x, sigma y, and tau xy. These are our x and y directions. So Cx actually is your direction of x, which is x direction, and Cy line shows y direction. Cx and Cy are at an angle of 180 degree. This is 2 theta, double angle. So actually x and y are at an angle of 90 degree. Okay. Now we have to keep our line CX or CY as a reference line and calculate all angles from CX or CY. In this circle, the horizontal line is normal stress. This is maximum normal, point A. This is minimum normal, point B. This is always origin. So sigma maximum, here is sigma minimum. Sigma maximum is equal to OA, which is OC plus CA. Sigma minimum is OB, which is OC minus BC. Okay, how we can calculate, point C has these coordinates, sigma average and 0, or point 3 was, draw a circle with C as center and CX as radius. This is Mohr circle. Okay. If CX is our horizontal axis, x-axis, and this is principal axis. So from x-axis to principal axis there is an angle. This is called 2 theta p. This is angle of principal plane with x-axis. But in circle we always have to show it in terms of double angle. Okay. How to find radius of the circle? Graphically, I am drawing perpendicular from point X on the horizontal axis. It meets here at point F. Okay, so Cx is our radius, which is equal to tan inverse of, you can use Pythagoras theorem here. The Cx is equal to square root of fx square plus cf square. Remember that fx is equal to tau xy. This is fx, vertical line from f to x. You can use this coordinate as our length. You have to, length is never a negative number, so we can just take its magnitude. And then what is CF? CF is equal to OF minus OC. OC is average, and OF, this point F has horizontal coordinates of sigma x and 0. The sigma x is same as the sigma x because they lie on the same line. That is sigma x minus sigma average. So we can find radius of the circle. Once we know the radius of the circle, we can calculate CA and BC. They both are radius actually. OC is already average stress, average normal stress. And once we have FX and CF sides, we can find theta P. 2 theta P is tan inverse Fx divided by CF. So we can find shear principal stress as well. The maximum shear stress at point D, this is tau maximum, it is equal to CD, and CD is radius, so we have already found radius here. And theta S, what is theta S? Theta S is angle from x-axis to the maximum shear plane. Here is our x-axis, Cx is our x-axis, remember. From here to here, this is 2 theta S. So it is equal to 2 theta P plus 90. 2 theta S is equal to 2 theta P plus 90 degree. Or we can say that theta s is equal to theta p plus 45 degree. So you can calculate theta s as well. So now we can use Mohr circle to calculate all kinds of principal stresses, maximum shear stress, principal plane and maximum shear stress plane. Okay, and then we can plot these elements as well. So we will use this theory. Okay, what more we can do with it? With Mohr circle, uniquely defined, the state of stress at any other axis orientation may be depicted. For example, if you are given an angle theta and you are asked to find normal and shearing stresses at an angle theta, you do not need to use expressions of sigma x, sigma y and tau xy dash, sigma x dash, sigma y dash and tau x dash y dash. You can use simply normal stress, simply Mohr circle. For a state of stress at an angle theta, with respect to the xy axis, construct a new diameter x dash y dash at an angle 2 theta with respect to x dash y. If you have been given angle theta, you must they must give you direction as well, counterclockwise or clockwise. For example, an angle theta clockwise. So this is your c axis, your x axis. This we can simply draw 2 theta here. If theta is given in circle, you have to convert it into 2 theta. At angle 2 theta, you have to plot another line with coordinates of x dash and y dash. X dash coordinates are, x coordinates were sigma x minus tau x dash tau xy. So here will be at x dash, it will be sigma x dash minus tau x dash y dash. Y coordinates were sigma y tau xy, so it will go to y dash, sigma y dash tau x dash y dash. Now we have to find these coordinates using trigonometry. How can we do? We can simply make it a triangle, find this angle, and then we can find sides. So we will do it in our numerical problems. We will move forward. Okay, some special cases. Mohr circle for plane stress, Mohr circle for centric axial loading. There is a unidirectional axial load P. So sigma in x direction is P over A. Sigma x is P over A. There is no force in y direction, so sigma y is 0. There is no shear force, so shear stress is also 0. Sigma x is P over A, sigma y is 0, tau xy is 0. So point x is sigma x minus tau xy. Sigma x minus tau xy. Sigma x is plus P over A and minus tau xy is 0. Okay, sigma y is, point y is sigma y plus tau xy. So again 0 0. You can draw x and y points. It doesn't intersect the horizontal line at any point. It is along the horizontal axis, so you can keep their center point as center of the circle and draw a circle using cx or cy as radius. And now we can see the sigma maximum is at point x, which is P over A, definitely. Sigma minimum is at point y, which is 0, and tau maximum is radius of the circle. So it is equal to, sigma maximum is also diameter of the circle, so sigma maximum divided by 2 is tau maximum. Sigma maximum is P over A, divided by 2 is P over 2A. We can draw this element here. Okay, the principal element is already this element, where there is normal stress but no shear stress, so this element is principal stress element. For shear stress, this is our principal line, horizontal line to this. So between principal and shear, there is an angle of 90 degree in the Mohr circle, so actual difference is 45 degrees. So we have an element rotated at 45 degree where tau is maximum, and when tau is maximum, normal is average. Similarly, for Mohr circle for torsional loading, in case of torsion, there is tau xy equal to Tc over J. There is no normal stress either in x or y direction. So sigma x and sigma y are 0. Tau xy is Tc over J. Point x has coordinates of sigma x minus tau xy. Sigma x is 0, minus tau xy is minus Tc over J. Sigma y is sigma y plus tau xy. Sigma y is 0, tau xy is Tc over J. You can simply draw. C is center point of these 2 points which intersects the horizontal axis. So you can draw a circle. Point A is our maximum stress. It is radius of the circle. Radius of the circle is simply equal to tau xy, which is Tc over J. And sigma minimum is also minus radius of the circle. So sigma maximum and sigma minimum are plus minus Tc over J. Tau maximum is at point Y. It is again Tc over J. And when tau is maximum, normal is average, which is equal to 0 in this case. So sigma dash is 0. This element which is given here, this element is maximum shear stress element. Tau is maximum here. Normal in this case is 0. Average stress in this case is 0. From principal to normal, there is a difference of 90 degree actually. In circle it is 90 degrees, so actually it should be 45 degree. So at 45 degree, you can plot another element which is sigma maximum and sigma minimum. Sigma minimum is negative, it is compressive. Sigma maximum is positive, it is tensile. These are two special cases. We will move towards a numerical problem. Example problem 7.02. Here we have been given sigma x equal to plus 50 megapascals. Sigma y is compressive, so it is minus 10. We have already solved this problem using formula earlier, so now we will solve it using Mohr circle, and you can compare the two answers. Tau xy is positive here because both the signs of both substitutes have same sign. So it is 40 megapascal positive. We have 2 points, x point, sigma x minus tau xy. Sigma x is 50 minus tau xy means minus 40. Y point is sigma y plus tau xy. So sigma y is minus 10 plus tau xy is 40. Statement of the problem is, for the state of plane stress shown, this is plane stress, 2-dimensional state of stress, construct Mohr circle. So we will use these 2 points x and y to construct Mohr circle and determine in part B principal planes. Principal planes means theta p. In part C, the principal stresses. Principal stresses means sigma maximum and sigma minimum. In part D, the maximum shearing stress and the corresponding normal stress. The maximum shear stress is tau maximum, and corresponding normal stress is sigma dash, which is equal to sigma average. So to draw the Mohr circle, we need these 2 points, x and y, 50 minus 40 and minus 10, 40. So we will draw it here. Here are horizontal and vertical axis. This is 50 minus 40 and y is minus 10, 40. Then joining x and y, it intersects the horizontal axis at point C. Cx is our radius. By using geometry tool compass, we can fix it at point C and draw a circle using Cx as radius. So this circle has intersected horizontal axis at point A and B. These 2 points are our sigma maximum and sigma minimum. Remember, I have already told you that Cx is our x-axis. So it is our reference axis. Horizontal line is our principal axis. So angle between them is 2 theta p. Okay. To find this radius, we have drawn a line from x point to horizontal axis, which intersects here at point F. F as coordinates of sigma x 0. So we can find CF and Fx here. Fx is vertical line. It is equal to tau xy, which is 40. Megapascals. Remember, the unit is megapascal. We are dealing with stresses. And CF is equal to OF minus OC. OF here is equal to sigma x. Sigma x is 50, and OC is sigma average. So sigma average is 20, becomes 30 megapascals. Sigma average is sigma x plus sigma y by 2. Sigma x and sigma y are known, so we can calculate it is 20 megapascal. CF I have already calculated it here, it is 30 megapascal. Fx is also calculated already, it is 40 megapascals. So we can find Cx using Pythagoras theorem in this triangle, which is equal to radius 30 square plus 40 square whole square root, it is 50 megapascal. So radius is known now. If radius is known, we can move forward and calculate principal stresses and principal plane. Hence, sigma maximum is equal to, this is sigma maximum, it is equal to OA. OA is further equal to OC plus CA. OC is average stress, sigma average. CA is radius. Both are known to us. Average is known and radius is known. We can put the values. 20 plus 50, it is 70 megapascals. Sigma minimum, here is sigma minimum. OB, which is equal to OC minus BC. OC is average, BC is radius. 20 minus 50, it is minus 30 megapascals. Tan 2 theta p. From this triangle, we can find 2 theta p. From x-axis to principal axis, this is 2 theta p. So 2 theta p is equal to tan 2 theta p is equal to Fx divided by Cf. Using trigonometry, you must know it. So Fx is already known, Cf is already known. 40 divided by 30, so theta p becomes 26.6 degree. One of the theta p is 26.6 degree. The next one must be by adding can be found by adding 90 degrees to the existing theta p, so it becomes 116.6 degrees. Okay, we can plot the element for principal stresses. Okay, the principal angle is 26.6 degree. It is positive, or if you do not know it is positive or negative, you can see here with x-axis the principal plane is counterclockwise. So you can plot here a counterclockwise angle with x-axis. Horizontal axis is our x-axis. So at theta p equal to 26.6 degree, we have plotted an axis, OA axis. This is principal axis, and you can see here at 26.6 degree with x-axis we have sigma maximum. This line goes to sigma maximum. So here it is, with this line it is sigma maximum. Then further at 90 degree, here is sigma minimum, which must be equal to its own variance. Sigma minimum is minus 30. Compressive stress, so it is already minus. Okay. In the next part, we were asked to find maximum shear stress and shear plane. So maximum shear stress, tau maximum is here at point D. Tau maximum is equal to CD. CD is radius, and radius is already known, 50 megapascals. Corresponding normal stress. When shear is maximum, what is corresponding normal stress? When shear is maximum at this point, the corresponding normal stress is here, which is average. Always remember that whenever it is asked to find maximum shear stress and the corresponding normal stress, the corresponding normal stress is always average stress. It is 20 megapascal, we already know it. Theta s, here, remember, theta s, all angles must be taken with x-axis. This is our x-axis cx. This is 2 theta s. From x-axis to maximum shear stress, 2 theta s. And this is 2 theta p. So 2 theta s, this is 2 theta p. 2 theta s is equal to 2 theta p plus 90 degrees. Theta s is equal to theta p plus 45 degrees. Okay, or you can see here it is theta p plus 45 degrees. So 71.6 degrees. Or if you take this one, this is also maximum shear stress, also 2 theta s. So 2 theta s here in this case is 90 minus 2 theta p. So it becomes theta s is equal to 45 minus theta p. So you will get the second angle here. Or you can simply add 90 or subtract 90 with this. You can find the second theta s. We have already plotted principal stress in the previous slide. Further from theta p to further 45 degree with theta p, we get theta s. And here we can plot an element where tau is maximum, 50 megapascals, and normal is average, which is 20 megapascals. Remember that you always have to draw the elements of shear stress and principal stress after calculating them. Even it is asked, either it is asked in the problem or not in the problem. Okay, the next is our sample problem 7.2. Sample problem 7.2 states that for the state of stress shown, determine the principal planes and principal stresses theta p and sigma maximum and sigma minimum in part A. Part B, the stress components exerted on an element obtained by rotating the given element counterclockwise through 30 degree. Rotate this element counterclockwise. This is counterclockwise direction. By 30 degrees, you will have another element, and you can find sigma x dash, sigma y dash, and tau x dash y dash here. So we know angle 30 degree. We have to use Mohr circle for this problem. Okay. Sigma x is given. It is 100 megapascals. Sigma y is given. It is 60 megapascals. Tau xy here you can see it is negative. I have already explained. You can apply your concept here, and it is negative 48 megapascal minus 48. Okay. X point is sigma x minus tau xy. Sigma x is 100 megapascal. Tau xy is minus 48, so minus tau xy will be plus 48. Point y, the coordinates are sigma y plus tau xy. Sigma y is 60 megapascals and plus tau xy. Tau xy is minus 48. Tau xy is already negative value, minus 48. Okay, so here is x point 100 plus 48, y point 60 minus 48. You can simply connect x and y using a line, and it will intersect the horizontal axis at point C. And then you can draw a circle by keeping C as center and Cx as radius. Draw a circle using a geometry tool. It will intersect the horizontal line at A and B. A is sigma maximum and B is sigma minimum. You can draw a perpendicular line from X to F to find the radius. So here we have CF and XF. We can find CF and XF using the method already explained in the previous problem. CF is equal to OF minus OC. F has the coordinates of 100, 0. 100 is same as this 100. 0 is because the second coordinate is 0 because it lies on the horizontal plane. So OF is equal to 100 minus OC. OC is average stress. Average stress is 80 megapascal. 100 minus 80. So it becomes 20 megapascal. Fx. Fx is simply this vertical line, and it is equal to 48. Radius Cx is equal to radius, and you can find it by Pythagoras theorem by putting all these values, and you can find radius here, which is 52 megapascals. Okay. Principal planes and principal stresses. Principal plane, how can you find principal plane? It is an angle of horizontal line with the x-axis. Horizontal line is here, CA, and x-axis is always CX. I have already told you CX is our x-axis. So with CX horizontal line has a clockwise angle 2 theta p. Clockwise, remember it, clockwise. Either you have to put a negative sign or write here clockwise. So it is XF divided by 10 2 theta p is XF divided by CF, 48 divided by 20, it becomes 2.4. Keep 10 inverse, take 10 inverse, and theta p will be 33.7 degree. And the next theta p will be, by adding 90 to it, it becomes 123.7 degree. Sigma maximum, it is equal to OA. Similar to the previous problem, we have found it OC plus CA, and by adding those two values, OC is sigma average, CA is radius. Sigma average plus radius. Similarly, sigma minimum is OB, which is OC minus BC. Sigma average minus radius, 28 megapascal. We can draw it 33.7 degree clockwise. So with x-axis clockwise 33.7 degree, you can draw an element. You know that with x-axis Cx clockwise you have sigma maximum. So here it is sigma maximum 132 megapascal. On the other axis it is sigma minimum 28 megapascal. Moving further, we were asked to find normal and shearing stresses at an angle of 30 degree counterclockwise. So we will draw from x-axis. X-axis is our Cx is our x-axis. We have drawn a counterclockwise angle of 60 degree. Theta was 30 degree, so 2 theta is 60 degrees. Okay, this angle is already known, which is theta p, already calculated in previous slides. 2 theta p is 67.4 degrees. This angle is 60 degrees, so this remaining angle phi must be equal to 180 minus 2 theta p minus 60. So phi is known, which is 180 minus 60 minus 67.4, it becomes 52.6 degrees. Okay, this point x dash has coordinates of sigma x dash minus tau x dash y dash. This point y dash has coordinates of sigma y dash plus tau x dash y dash. Okay, we can draw a perpendicular from x dash on the horizontal axis, x dash k, using this triangle c k x dash. We can find these coordinates sigma x dash and tau x dash y dash. Similarly, from this triangle C, L and y dash, we can find the coordinates sigma y dash and tau x dash y dash. Sigma x dash is equal to OK. Sigma y dash is equal to OL. And tau x dash y dash is equal to Ly dash or Kx dash. Okay. So with this triangle, sigma x dash is equal to OK. OK is further equal to OC minus CK. OC is average stress and CK or KC can be found from the triangle. It is base of the triangle. So it is radius into cosine of angle phi. 52 into cosine of 52.6 degrees. Similarly, sigma y dash is equal to OL. OL is equal to OC plus CL. OC is average. CL from the triangle CLY dash, it can be calculated. CL is 52 cosine of 52.6 degrees. Similarly, tau x dash y dash is equal to Kx dash. It is perpendicular side of the triangle, which is 52 sine of 52.6 degrees. Simple trigonometry has been applied. So you can calculate sigma x dash, sigma y dash and tau x dash y dash. You do not need any formula or expression to remember, and simply using graphical method we have calculated sigma x dash, sigma y dash and tau x dash y dash. We have to plot this element. So simply with x-axis, with the horizontal axis, counterclockwise 30 degrees, there is another axis OX dash. You have plotted an element here with x-axis 30 degree. On this axis you have sigma x dash, which is 48.4 megapascal. Perpendicular to it is sigma y dash, which is 1.6 megapascal, and tau x dash y dash is 41.3 megapascals. Okay, we will move further. Next is general state of stress in 3 dimensions. In 3 dimensions, you can calculate transformational formulas using a similar method which we have used for 2 dimensions, but now we have 3 dimensions, so you have to draw 3 components of every force. And you can also use direction cosines here. Lambda x, lambda y and lambda z. Lambda x is cosine of the angle with x-axis, lambda y is cosine of angle with y-axis, and lambda z is cosine of the angle of any force with z-axis. So here is a part of the tetrahedral part of the cube. If you slice a cube into a tetrahedron and you have sigma x, sigma y and sigma z, similarly tau xy, tau yx and tau xy, tau yz and tau zx, and then similar to the wedge problem, you can draw rectangular components of each force. It is very difficult to do it here on the screen. It will not be visible. The forces cannot be drawn here so easily, so you can do it by yourself. And perpendicular to this surface is direction n. Similar to our previous method, you can find sigma n here. I do not want to repeat here. It is not included in your course. Okay, but I am just doing it because we have to draw a 3D Mohr circle. And this is normal stress in direction n for 3-dimensional state of stress. Here sigma x, sigma y and sigma z are normal stresses in x, y and z direction. Tau xy, tau yz and tau zx are shear stresses. Lambda x, lambda y and lambda z are direction cosines. If in case the shearing stresses are 0, these three terms will be 0, and we will get sigma n as this. Now sigma x, sigma y and sigma z are replaced with sigma a, sigma b and sigma c. These sigma a, sigma b and sigma c are normal stresses when shearing stresses are 0, so they are actually principal stresses. When the value of normal stress, when shearing stress is 0, the normal stress is principal stress. So these three are principal stresses, and they lie along three principal axes, OA, OB and OC. I am not going into detail of this transformation. I am simply using it for a Mohr circle. You must know that the three principal stresses sigma A, sigma B and sigma C exist when the shearing stresses are 0. So we will use these three principal stresses to draw a Mohr circle in 3 dimensions. A 3-dimensional Mohr circle is never a 3-dimensional circle or a sphere. It is just a combination of 3 circles. In 2 dimensions, we used to draw a single circle. It is for xy plane or xz plane or yz plane. In a single plane, we have only a single circle. So in 3 planes, we have 3 circles. Separate circle for plane xy, a separate circle for plane yz, and a separate circle for plane zx. So for 3 principal stresses, sigma A, sigma B and sigma C, you can draw 3 circles in such a way that each circle is tangent to the other circle. These 2 circles are tangent at point A, here at point B and here at point C. At point A, we have sigma maximum. At point C, we have sigma minimum. And sigma B is between sigma maximum and sigma minimum. We have 3 principal stresses. Tau maximum is always radius of the outer circle. Remember that 3-dimensional Mohr circle is always contains always 3 circles. The outer circle is tangent to the 2 circles, inner circles, and the 2 inner circles are tangent to each other and also tangent to the outer circle. Radius of the outer circle is always tau maximum, which is equal to half of the difference of sigma maximum and sigma minimum. In your course, we will only discuss 3-dimensional Mohr circle for plane stress elements. For a plane stress element, we only have two-dimensional state of stress. For a plane stress element, we have sigma x, sigma y and tau xy. This element may rotate around z-axis. Since it is a plane stress element, all stresses in z direction are 0. So principal stress in z direction will also be 0. Sigma z is 0, so sigma c is 0. We have to find sigma a and sigma b. Okay. Similar to the previous methods, using Mohr circle or using formulas, you can find sigma a and sigma b, or sigma maximum and sigma minimum. Once we find sigma a and sigma b, we can draw their circle anywhere. You must know that this is sigma a or sigma b or sigma minimum and sigma maximum. Sigma c in plane stress element is always 0, so it will be here. So we know the second circle will be here it will be a dotted one, and the third will always be around the two circles. So a plane stress element, Mohr circle for a plane stress case will always be like this: three circles where two are dotted and one is solid. The solid circle is in plane circle. The dotted circles are out of the plane circles. This in plane circle represents this given state of stress: sigma x, sigma y, tau xy. The other two circles represent the other two planes. This one, the solid circle, represents xy plane. The other two circles represent yz and xz planes. Now, there are two special cases. Remember that in a plane stress, Mohr circle for a plane stress state will contain one solid circle which shows in plane deformation. It is an in plane circle. In plane transformation, sorry. So it is an in plane circle. The dotted circles are out of the plane circles. So it is possible that either the point A and B may have opposite signs. For example, A is positive, B is negative, or A can be negative, B can be positive. So the outer circle will be, in this case, will be solid, because circle representing the non-zero principal stresses is always in plane circle. So A and B are have opposite sign. They are non-zero stresses. The third stress will always be zero. Third principal stress will always be zero in plane stress case. So the two non-zero stresses are passing through. A circle passing through the non-zero stresses is solid circle, which is in plane circle. The other two circles, which connects point sigma B and sigma A with the zero stress sigma C, they are dotted circles, and they denote out of the plane circles. In this case, sigma A is maximum, sigma B is minimum, and tau maximum is radius of the outer circle. So this tau maximum is also tau maximum in plane. Tau maximum in this case is tau maximum in plane, and it is equal to sigma A minus sigma B divided by 2, radius of the outer circle. Okay. If you are asked to find tau maximum, you can simply find tau maximum in plane. If you are asked to find tau maximum out of plane, it is specific. There are two out of plane circles, this one and this one. The greater circle has greater radius, so this will be tau maximum out of plane, if it is asked. Okay. Similarly, if you have another case where both point A and point B have same sign, they are on the same side of the origin. Now they are non-zero stresses. Circle, solid circle again denotes the in plane circle, and then there is another zero stress. It lies out of the circle. In the previous case, the zero stress or the third principal stress was inside the in plane circle. In this case, it is outside the in plane circle. So we will just join point B with the zero stress with a dotted circle, and then point A with the zero stress again with a dotted circle. In this case, the greater circle is, the outer circle is out of the plane circle. This tau maximum is actually tau maximum out of plane. If you are asked to find tau maximum, in this case it is out of the plane tau maximum, and it is equal to radius of the bigger circle, which is half of sigma maximum or sigma A. If you are asked to find tau maximum in plane, so definitely it is at point B. At point D, it is tau maximum in plane, and this time it is equal to radius of the solid circle, it is sigma A minus sigma B divided by 2. Okay. So if you are asked to find tau maximum definitely it is out of plane, because bigger circle is always maximum, has always maximum radius. So only tau maximum is out of the plane tau maximum. If it is specified to find in plane tau maximum, then you have to use this expression. Okay. In all the cases, the maximum shearing stress is at 45 degrees with the plane of stress. This is maximum shearing stress. It has, this angle is 90. So if it in the circle, it is in the circle it is 90. So actually it is at 45 degree with the plane of stress. Similarly, in the previous case, this is maximum shear. Maximum shear is here. This angle is 90. So actually it is 45 degree. Okay, so we will solve a concept application here. Concept application number 7.3 from the textbook. For the state of stress shown, determine the three principal planes and principal stresses. And principal plane and principal stresses means theta p and sigma a, sigma b, and sigma c. Sigma c is definitely 0. It is state of plane stress. We have to find sigma a and sigma b actually. In part B, the maximum shearing stress, tau maximum. They haven't mentioned it as out of the plane or in plane, so we will see whichever is the outer circle, it will be tau maximum. So in order to draw a three-dimensional circle, first we have to draw a two-dimensional circle with the given data. Given data is sigma x is equal to 6 ksi, sigma y is equal to 3.5 ksi, and tau xy is minus 3 ksi. You know how the minus or positive sign is defined. Point x will be sigma x minus tau xy. So it is 6 plus 3. Tau xy is already negative. So minus tau xy will be positive. Point y is sigma y plus tau xy. So plus tau xy is, sigma y is minus 3, sigma y is 3.5. And plus tau xy is negative 3. So here is point x and point y. We can simply join them. It will intersect horizontal line at point C. It is our center point, which denotes average stress. 4.7 ksi. You can draw the circle. This is our in-plane circle drawn with the given data, sigma x, sigma y, and tau xy. You can simply find maximum stress and minimum stress from it, which will be our sigma a and sigma b both have same sign. In this case, sigma a and sigma b both have same signs. So using our previous methods, you can find it. I will not explain it again. Sigma a and sigma b are here. Now theta p can be found with fx tan to theta p equal to fx over cf. It is our x-axis, cx is our x-axis, so this is our 2 theta p clockwise with x-axis. So it is clockwise. You can draw this element here with x-axis. It is clockwise theta p 33.7 degrees, and then you can plot the stresses. Now we have already plotted two-dimensional circle, which is in-plane circle. So the third stress in the state of plane stress is always 0. So third stress is here, always with the origin, remember it. So join it with point B using a dotted circle, and then with point A using another dotted circle, like this. In this case, our maximum stress is out of the plane. It is of the dotted circle. Remember it, out of the plane circles must be dotted one in a for a Mohr circle, in case of Mohr circle for a state of plane stress. So this one has radius equal to sigma a by 2. This is sigma a by 2. So it is 8 divided by 2, 4 ksi. If you are asked to find sigma maximum in plane, then this circle radius is tau maximum in plane, but it has not been asked. We were asked to find sigma maximum only. So maximum among these two is radius of the outer circle, which is out of the plane. Always radius of the outer circle is tau maximum. If it is not mentioned out of the plane or in plane, so outer circle radius is tau maximum. In this case, it is dotted, so it is out of the plane. If you are asked to find tau maximum in plane, it is radius of the solid circle, which will be sigma A minus sigma B divided by 2. You can calculate it by yourself. You know sigma A and sigma B from our previous slide. Okay. Our next topic is yielding criteria for ductile materials under plane stress. Before that, we have already discussed Mohr circle in details. We can find principal stresses, principal plane, maximum shear stress, the corresponding normal stress, and maximum shear stress plane using the Mohr circle. So now we are moving further towards yielding criteria. What are yielding criteria? Yielding criteria are simply yield means it is for ductile materials. The brittle materials do not yield. If we draw a stress strain diagram, here is sigma yield for ductile materials. For brittle materials, we do not have any sigma yield. They directly fracture and they have sigma ultimate. So we cannot use yielding criteria for brittle materials. Yield criteria for ductile material or yielding criteria for ductile material is a failure criteria. How a ductile material fails. So if we have a unidirectional load, we know that there is only one principal stress in the direction of the load, and when the principal stress reaches the yield stress, it will fail. The part will fail. But if we have a two-dimensional state of stress, sigma x, sigma y, and tau xy, we do not know which when the structure will fail, because either of the stress can reach yield stress before that. And now we have, in two-dimensional case, we have two principal stresses, sigma A and sigma B. So for such cases, we have to define failure criteria for materials under multidimensional loads, not a unidirectional load. So on the basis of principal stresses, we can find how a material will fail and when a material will fail. So we define failure criteria for ductile materials. The first failure criteria for ductile materials which we are going to discuss is maximum shearing stress criteria, or Tresca criteria. Tresca is the name of the person who has introduced this theory, this criteria. Structural component is safe as long as the maximum shearing stress is less than the shearing stress in a tensile test specimen at yield. Similar to normal stress and normal strain, we have shearing stress and shearing strain graph. There is tau yielding at yield point. So tau maximum must be less than tau yielding. If tau maximum is less than tau yielding, the structure is safe. If tau maximum exceeds tau yielding, the structure will fail. The tau yielding is almost equal to sigma yield by 2, half of sigma yield for ductile materials. Remember, this is from literature that tau yielding is half of sigma yielding, almost half of sigma yielding. So tau maximum can be found from Mohr circle. We have calculated tau maximum from Mohr circle. Here, tau maximum from Mohr circle, or for 2 dimensions, we can calculate tau maximum from a Mohr circle. Here we have calculated tau maximum. In a previous problem, I will show you here tau maximum from a Mohr circle. So tau maximum is radius of the circle. For a Mohr circle, tau maximum is radius of the circle. If sigma A and sigma B both have same sign, so tau maximum should be half of the sigma A or sigma B. If they have opposite sign, so tau maximum is sigma A minus sigma B divided by 2. So first we have to find sigma A and sigma B using Mohr circle, and if both of them are same sign, so tau maximum should be less than half of sigma A by 2 or sigma B by 2, whichever is maximum. If sigma A is maximum, tau maximum is half of sigma A by 2. If it is sigma B is maximum, it is sigma B by 2. So either sigma A by 2 should be less than sigma Y by 2, or sigma B by 2 should be less than sigma Y by 2. Sigma A should be less than sigma Y, sigma B should be less than sigma Y. Whichever is greater among them, that is applicable. Mostly sigma A is greater. If sigma B and sigma A have opposite signs, sigma A minus sigma B divided by 2 should be less than sigma Y by 2, or sigma A minus sigma B should be less than sigma Y. If you want to find factor of safety using this criteria, so you can simply use these expressions. Sigma A is equal to sigma Y by factor of safety. If sigma B is greater, then whichever is greater among them, among sigma A and sigma B, you can use that expression. Or if they have opposite signs, then sigma A minus sigma B is equal to sigma Y by factor of safety. This sigma Y, capital Y, is for yielding. Okay, do not confuse sigma Y with sigma Y. This small y is for y direction. This capital Y is for yielding. Okay, so when we have to find factor of safety, we can simply replace them with equality sign. Okay, if sigma A and sigma B both are positive, same sign, positive, so they both must not, this axis is sigma A axis, this is sigma B axis, they must not exceed sigma yield. A constant value sigma yield and a constant value sigma yield, they intersect here. If they both are negative sign, same but negative, negative sigma yield. If they have opposite sign, sigma A is negative, sigma B is positive, this axis, here is a linear expression. This line represents this linear expression, and in the fourth quadrant, this line represents this linear expression. In this envelope, if any point lies within this envelope, it is safe. If any point lies out of this envelope, it is failed as per maximum shearing stress criteria. Okay, if we move forward, there is another criteria, which is maximum distortion energy criteria, or von Mises criteria, the person who has introduced it. Von Mises criteria. Structural component is safe as long as the distortion energy per unit volume is less than that occurring in a tensile test specimen at yield. Whenever a material is deformed, it absorbs energy. The area under a stress strain curve denotes strain energy per unit volume absorbed by the material. So if it is, here is sigma y, strain energy absorbed, strain energy per unit volume absorbed until sigma y is uy, small uy. So if the distortion energy is less than uy, you will discuss this strain energy in detail in chapter number 11. So now it is enough here. If ud, distortion energy, is less than uy, energy required to obtain yielding or to achieve yielding. So ud from chapter number 11, you will find it is 1 over 6g sigma a square minus sigma a sigma b plus sigma b square. I am not going to explain it here. This expression is as it is, you have to use it. Okay, in a unidirectional tensile test, one of the sigma A and sigma B, one of them is 0 and the other is equal to sigma y at yielding. So here we will replace sigma A as sigma y at yielding. Sigma I is equal to sigma y. sigma b is 0 in unidirectional test. So we get this expression, which is expression for von Mises criteria. Sigma a square minus sigma a sigma b plus sigma b square is less than sigma capital Y square, sigma yield square. If you want to find factor of safety, simply divide sigma y by factor of safety and take whole square because it is sigma y square, so factor of safety square. You can simply replace this with equality sign if you want to find factor of safety. So if this left hand side is less than the right hand side, the material is, or the structure is safe as per maximum distortion energy criteria. If it is not less than the right side, it is not safe. So this is an elliptic equation of an ellipse, and if we draw a curve, or if we draw this expression between sigma a and sigma b on a graph paper, it will be an elliptical shape. This is a little different than the previous envelope of maximum shearing stress criteria. If we draw both of them on the same paper, it will be like this. The inside envelope with the red color is it denotes maximum shearing stress criteria. The outer one denotes maximum distortion energy criteria. Any point inside the envelope, for example this point, it is safe as per both the criteria. Any point outside both the envelopes is unsafe as per both the criteria. Any point between them, like here, this point, it is safe as per von Mises criteria, but it is unsafe as per Tresca criteria or maximum shearing stress criteria, because this point exists within the envelope of von Mises criteria, but it is outside the envelope of Tresca criteria. It means Tresca criteria is a bit harsher or a bit conservative as compared to von Mises criteria. There are some state of stress which are safe as per to von Mises or maximum distortion energy criteria, but they are not safe as per maximum shearing stress criteria or Tresca criteria. So Tresca criteria is considered conservative as compared to von Mises criteria. But now we have to find either which one of them is correct or applicable actually. So if we see the literature, the von Mises criteria has been applied on ductile materials and it is effective. It means the von Mises criteria is safe as compared is safe, and it cannot be called failed criteria. If von Mises is safe, definitely Tresca is safe, because it is the Tresca criteria is even conservative as compared to von Mises criteria. So von Mises criteria can be applied. It is safe. It depends upon your application. If you need higher factor of safety, you can apply Tresca criteria. If you need lower factor of safety, you can apply von Mises. Comparatively lower factor of safety, you can apply von Mises criteria. Both of them are applicable. The Tresca criteria will cost you more because it is conservative and it has higher factor of safety. You will need to consume more material as compared to von Mises criteria. Both these criteria are yielding criteria, and they can be applied to ductile materials only. Okay, let us move further. Our next criteria, or our next topic, is fracture criteria for brittle materials under plane stress. As discussed earlier, the brittle materials do not undergo yielding, they directly fracture, and there is no permanent deformation in brittle materials. That is why fracture criteria are applied to the brittle materials. The already discussed ductile material yielding criteria cannot be applied to brittle materials. Okay, because the brittle materials fail suddenly through rupture or fracture in a tensile test. Okay, the first one among fracture criteria is maximum normal stress criteria. It is also called Coulomb's criteria. A structural component is safe as long as the maximum normal stress is less than the ultimate strength of the tensile specimen. Ultimate strength. Maximum normal stress is less than the ultimate strength. Maximum normal stress is actually principal stress, sigma maximum. So sigma maximum, if either it is sigma A or sigma B, whichever is maximum, it should be less than sigma U. If maximum is less than sigma U, the minimum is automatically less than sigma U. So sigma U is ultimate. You remember it. In brittle materials, we have used sigma U. In ductile materials, we have used sigma Y. It is for ductile materials yielding, and it is for, so you will always find sigma U in fracture theories, fracture failure theories. Fracture theories are brittle materials. Okay, so both sigma A and sigma B should be less than sigma U. If we draw it here between sigma A and sigma B, sigma A should be less than sigma U. In compression, sigma A should be less than minus sigma U. Again, in tension, sigma B should be less than sigma U. Sigma B should be less than minus sigma U in compression. These are simply constant values. Sigma U is a constant value. So if we draw lines here, they intersect each other at some point, and we have got an envelope. Any point inside this envelope is safe, and anything outside the envelope is unsafe as per the maximum normal stress criteria or Coulomb's criteria. This criteria is also called maximum principal stress criteria or principal stress criteria. Okay, now there is a drawback of this criteria, because they have considered sigma U in this criteria. There is no, they are not differentiated between tensile or compressive values. And this criteria is based on assumption that the ultimate strength of material is same in tension and compression, which is not actually the case. In reality, the tensile compressive stress and the tensile ultimate strength and the compressive ultimate strength of brittle materials is not same. The brittle materials have higher compressive ultimate strength as compared to tensile ultimate strength, because the metal materials already contain micro cracks or nano cracks, nano flaws, and when we compress them, the cracks close and the material is stronger as compared to its strength under tensile loading. When we put material under a tension, the cracks open and the material fail earlier as compared to the compressive load. So this theory is not applicable to materials under compression loading. So there is a drawback. Then to counter it, we have another theory, Mohr's criteria. The Mohr's theory of failure is used to predict fracture of a material having different properties in tension and compression. So the shortcoming of the previous theory has been covered in this theory. Rest of the things are same. If both principal stresses are positive, the state of stress is safe as long as sigma ultimate is less than sigma A is less than sigma ultimate tension and sigma B is less than sigma ultimate tension. T is for tension. So if both the stresses are positive, sigma A and sigma B both are positive, they are tensile, so they both should be less than sigma ultimate under tension. If both of them are negative, if both principal stresses are negative, state of stress is safe as long as sigma A is less than sigma ultimate and sigma B is less than sigma ultimate compression, sigma UC. For negative principal stresses, we will use these two expressions. For positive, we will use these. Whichever is greater among sigma A and sigma B, it should be less than sigma ultimate in tension and as well as in compression. So here, if we draw Mohr circle for a simple tensile test of a material, you will get this outer circle. Sigma ut is maximum principal stress under a tensile load. Sigma uc is for compressive load. You will get this circle. Now you are testing your own material. It will have sigma A and sigma B. If you are testing your material and the circle is within this outer circle, the outer circle is under a standard tensile test. This circle is under a standard tensile test. This circle is under standard compressive test. Your material, if your structure is the Mohr circle of your structure is within the outer circle, both sigma A and sigma B are less than sigma ultimate tensile. It is safe. In case of compression, if your structure, the Mohr circle of your structure is within this circle, both sigma A and sigma B are within the circle, they are less than sigma uc, so it is safe. For example, if there is a circle of this type, if you are doing if your structure is under compression and you draw a Mohr circle and it is of this type, sigma A and sigma B, this sigma B is greater than sigma uc, ultimate compression strength, so the material is no longer safe. If the circle is like this, if the circle is here, both sigma A and sigma B are greater than sigma uc, so the structure is not safe. Either one or both of them are greater than sigma uc, the structure is not safe. Under tension, if it is out of this circle or if it is here like this, any one of the principal stresses is greater than sigma ultimate tension, so the structure is not safe. Okay, so we can mathematically use these expressions. In graph, you can see sigma A and sigma B. Horizontal axis shows sigma A, the vertical axis shows sigma B. If both of them are positive, it is first quadrant. Sigma A should be less than sigma ultimate and sigma B should be less than sigma ultimate, these two constant lines. So all the points should be within this area. In case of compression, both should be less than sigma uc. Sigma uc is greater than sigma ut. I have already explained it. So anything within this area is safe. So for tension, we have this envelope. For compression, we have this envelope. For pure tension load, for pure compression load, the points should be within this envelope. Anything out of this envelope, here, or here, they are unsafe as per the Mohr's failure criteria. Now, if the previous diagram or the previous discussion was for pure tension or pure compressive loading. Now, if we have kind of both tension and compression, like torsion load. So we have a Mohr circle for torsion as well. This circle was previously discussed for pure tension. This is for pure compression. This circle, the middle one, is for torsion, which is under both compression and tension. So we can draw a circle like this. For sigma A and sigma B having opposite signs, torsion test, a circle centered at O is drawn, representing the state of stress corresponding to the failure of the torsion test specimen. According to Mohr's criteria, a state of stress is safe if it is represented by circle located entirely within the area bounded by the envelope of the circle. Now we can draw lines curves tangent to both these three circles. This curve is tangent to all the three circles. This curve is tangent to all the three circles. Anything within this envelope, any circle, any Mohr circle within this envelope, it is safe. Anything out of this circle, any principal stress or any Mohr circle, for any case, for example here, it is failed. For example here, it is failed. they are outside the envelope. Similarly here, similar to the previous diagram, this quadrant shows opposite values of sigma A and sigma B. So within this envelope, anything, if both the principal stresses are positive, it should be within this envelope here. If both are negative, it should be within this area. If one is positive, sigma A is positive, sigma B is negative, it should be here. If sigma B is positive, sigma A is negative, it should be here. Anything outside this envelope is not considered safe. It is failed as per the Mohr's failure criteria, Mohr's fracture criteria. This is applicable to brittle materials only because it deals with ultimate strength, either in tension or compression. Here is a sample problem number 7.4. The state of plane stress shown occurs at a critical point of a steel machine component as a result of several tensile tests. Tensile yield strength sigma y. Tensile yield strength sigma y, so it means it is a ductile material. Sigma y yield strength is for ductile material. For the grade of steel used, determine the factor of safety with respect to yielding. With respect to yield means you have to apply yielding criteria. Even if sigma y is given, you can apply yielding criteria. Maybe in a problem both of them are given, sigma y and sigma u, ut and uc. Again, you have to see if it is a ductile material, you will use sigma y. If it is a brittle material, you have to use sigma u. Okay, in the part A, it is asked using maximum shearing stress criteria. In part B, using maximum distortion energy criteria, von Mises criteria. What we have to find? Factor of safety. Okay, here is the state of stress given. Sigma x is 80 megapascal. Sigma y is 40 megapascal. And tau xy is 25 megapascals, positive 25. You have to draw Mohr circle to calculate sigma A and sigma B. Or you can use expressions for sigma maximum and sigma minimum. It is your option. If it is mentioned in your exam to use Mohr circle, then you have to use Mohr circle. Most probably, usually you are asked to draw Mohr circle. And if it is not mentioned, then it is your choice. So I recommend you to draw Mohr circle. Here it is already solved using the formula sigma A and sigma B. This expression is already has been discussed. So we can find sigma A and sigma B 85 and minus 45 megapascals. Since both of them have opposite signs, using maximum shearing stress criteria for opposite sigma A and sigma B, we have this expression already discussed. So by putting the values of sigma A and sigma B, capital Y, it is given, it is yield strength. So you must keep all the units same. If it is megapascal, so sigma y should be in megapascal as well. So factor of safety becomes 1.92. 192 is too much. Whenever you calculate factor of safety, it should be reasonable, within reasonable limits. So 1.92, it is reasonable. Using maximum distortion energy criteria, we have its expression. We have all the values, sigma A, sigma B and sigma y. We can calculate factor of safety. Graphically, we can verify it or we can calculate again by drawing the envelopes here. We know the outer envelope, the ellipse is for maximum distortion energy criteria. The inner one is for Tresca criteria or maximum shearing stress criteria. So this is 0, 0. Sigma A and sigma B are given 85 minus 45. 85 minus, this is horizontal axis sigma A, vertical is sigma B. So 85 minus 45 point, it is here. This point H at in quadrant number 4. So we can draw the line OH and then further extend it. It will intersect the outer envelope at point M, 1 mices, M denotes mices, 1 mices, and the inner envelope, Tresca envelope at point T. Now we can measure the length of this line, the portions OH, the portion OT, the portion OM. As per Tresca criteria, this structure is safe between O and T and OT, but it lies at OH. So we can find factor of safety OT over OH. OT is our maximum limit, OH is our current position. So by measuring the length of these two lines, if you draw it on a graph paper and by scale, using a scale, you can find the length of these two portions. It must be 1.92 as calculated earlier. Similarly, if you find the length of OM, this structure is safe until the point exceeds point M as per the 1 mices criteria. So OM is our maximum limit. Currently the structure is at OH. So OM or OH, it must be 2.19 as calculated using the formula earlier. So graphically you can think about it, you can verify your answers as well. You may be asked to calculate it graphically as well. Okay, let us move further. Our next topic is stresses in thin-walled pressure vessels. Okay, this is very important topic and very interesting one as well. Thin-walled pressure vessels. What is the difference between thin and thick-walled pressure vessels? In thin-walled pressure vessels, the thickness is so small that there are no stresses or negligible stresses in radial direction. In pressure vessels, we usually have three directions. The hoop direction, hoop or circumferential direction, the longitudinal direction, and the radial direction. So for thin walled pressure vessels, there is no stress in the radial direction. No stress. Because the wall thickness is so small that in the radial direction there is negligible stress. This type of state of stress is called plane stress. So the thin wall pressure vessels are under plane stress conditions because their wall thickness is so small that along in the thickness direction the stresses are negligible. By definition, you can say how you can differentiate between a thin wall and a thick wall pressure vessel. If you find the ratio between radius and thickness of the cylinder, if the ratio between the mean radius, means mean of outer and the inner radius, if the ratio between the mean radius and the thickness, the wall thickness is greater than 10, the pressure vessel is thin wall pressure vessel. If the ratio of mean radius to the thickness of the cylinder is less than 10, the pressure vessel is thick wall pressure vessel. Okay, it means the thickness should be very small. So in thin wall pressure vessels, there are only hoop stresses and longitudinal stresses. Hoop is along the circumference and longitudinal means along the length. So here is a cylinder. Cylinder means it has a length and it has a radius. So along the length we have sigma 2, along the circumference we have sigma 1. Sigma 1 is hoop stress, sigma 2 is longitudinal stress. If we cut this cylinder parallel to its length and we take a segment of length delta x, due to internal pressure, the thin wall pressure vessels or the thick wall pressure vessels are always under internal pressure. If the internal pressure is small p, the internal pressure acts towards the walls of the cylinder. So this internal pressure P is perpendicular to this area, rectangular area, and in the wall thickness, in the thickness portion of the cylinder, there is a resistance to this pressure. It is sigma 1 along the circumference. So if we convert these stresses or this pressure to the force, we have to multiply them with the area. So let us multiply this pressure with its area, dA, and sigma with its, these two dAs are different. Let me call it dA1 and this is dA2. Okay, do not confuse it. This area, the area in shaded color, it is for pressure P. It is a rectangular area. So by using summation of forces in z direction equal to 0, sigma 1 into its area dA. This area is delta x into thickness T, but 2 times thickness, because here we have two areas, this area and this area. So sigma 1 into 2 times T into delta x minus P is in opposite direction. Sigma and P are always in opposite direction. Minus P into this area is this length, which is 2r, into thickness into delta x, the length of this segment, delta x. So 2r into delta x. If we simplify it, sigma 1 becomes PR over T. Similarly, if we cut this cylinder parallel to its cross section, the internal pressure goes inside the cylinder. This line, this line, this line, this internal pressure. Okay, P. This P acts on a circular area, and then in the wall thickness, this area, there is stress, okay, sigma 2. So both the areas are different. This is, let me call this is dA1, and this one is P into dA2. So area of a circle is pi r square, internal r, remember this r is inner radius, here also r is inner radius. Okay, the outer radius, the outer the wall thickness, the wall thickness area is 2 pi r is its circumference. If we cut the cylinder and straighten it up, it is like this. This is 2 pi r and this is thickness. So 2 pi r T. Stress and pressure are in opposite directions, so there is negative sign with the pressure. Sigma 2 becomes PR over 2T. Sigma 1 and sigma 2. Sigma 2 is half of sigma 1, or sigma 1 is 2 times sigma 2. So hoop stress is greater than longitudinal stress. For thin wall cylinders, hoop stress is twice the longitudinal stress. Okay, if we draw more circle, hoop stress is greater than, okay, in this case we can see both these stresses are normal stresses. There is no shear stress, so they are actually principal stresses. Hoop and longitudinal stresses are principal stresses. Point A denotes hoop stress, point B denotes longitudinal stress. Point A is sigma 1 OA and OB is sigma 2. Sigma 1 is half of, sigma 2 is half of sigma 1. So OB and BA, both portions are equal, sigma 2 and sigma 2, because sigma 1 is 2 times sigma 2. These two stresses are non-stresses. They are non-zero stresses. So if we draw a circle along these two stresses, it will be a solid circle. It is an in-plane circle. It is a this is a state of plane stress. So all other circles, both of the other circles will be dotted circles out of the plane circles. These two circles must have same diameter, because sigma 1 is 2 times sigma 2. So these two have same radius. The outer circle is a denotes the outer circle gives us maximum shear stress, and in this case the outer circle is out of the plane circle. So this tau maximum is out of plane, which is equal to radius of the outer circle, which is equal to sigma 1 by 2 or sigma 2. Similarly, if you are asked to find in plane shear stress, this is tau maximum in plane, and it is equal to sigma 1 minus sigma 2 by 2 or sigma 2 by 2 or PR over 40. This will be PR over 2T. So this is a standard Mohr circle for thin wall cylinders. You may be asked to draw Mohr circle for thin wall cylinders, so you can draw it like this. Okay, for in all the problems, the shape will be same. Numerical values may differ. Okay, stresses in thin wall pressure vessels, and if the pressure vessel is a sphere. In sphere, we do not have any length. In all direction, there is radius. So sigma 1 and sigma 2 both are circumferential in this case, and they both are same. For sphere, direction 1 and direction 2 both are circumference. So sigma 1 is equal to sigma 2, similar to the previous one. If we cut it, and we can see there is a radius, pressure is acting on a circular area. So similar to the longitudinal stresses case in thin wall cylinders, we can find sigma 1 and sigma 2 both are same. We can find using this diagram, they both are PR over 2T. We can draw a Mohr circle for it as well. Sigma 1 and sigma 2 principal stresses, non-zero principal stresses, both are same. If they both are same, they both lie at a same point, point A and point B, both are same. If they both are same, the radius of this circle is 0, so this circle is actually a point. You will denote it as a point, as a dark point. So this point shows in plane circle. This is in plane circle, and tau for this circle is tau maximum in plane is 0. Always for spherical pressure vessels, tau maximum in plane will be 0. Okay, then the other two circles both are same, both coincide with each other. The third principal stress is 0 at point O. So circle between B and O, and A and O both are same, the dotted one. This is out of the plane circle. Tau maximum is actually tau maximum out of the plane. This is out of plane. Out of plane shear stress is equal to half of the sigma 1. Sigma 1 is diameter of this circle, and radius of the circle will be tau maximum. Sigma 1 and sigma 2 both are same. So tau maximum in plane is 0, tau maximum out of plane is half of sigma 1 or PR over 4T, because sigma 1 is PR over 2T. So this circle is a very interesting one. Here is a dot and only one dotted circle. Dot represents n-plane circle for thin wall spherical pressure vessels. Okay. Next is sample problem 7.5 from the textbook, a very important one, a very interesting one as well. A compressed air tank is supported by two cradles as shown, this one and this one. One of the cradles is designed so that it does not exert any longitudinal force on the tank. So it means when the tank expands, it can move in the longitudinal direction along one of the cradle. Okay. The cylindrical body of the tank has 30-inch outer diameter, and it is made of 3 by 8-inch steel plate by butt welding along a helix that forms an angle of 25 degree. This is cylindrical portion. It has outer diameter of 30 inches, and wall thickness, this is thickness for cylindrical portion, 3 by 8 inch. And this weld, a steel plate is helically welded, and the welding angle is given helical angle is 25 degrees, yes. Okay, the ends, this end and this end, and they are spherical. The end caps are spherical and have a uniform wall thickness of 5 by 16. This is thickness for spherical portion. This earlier one was for longitudinal portion, cylindrical portion. Okay, the internal pressure P, small p, it is given as 180 psi. In part A, we have to determine the normal stress and maximum shearing stress in spherical portion. In spherical portion, the normal stress is sigma 1 and sigma 2, both are same, this is unknown, and maximum shearing stress, tau maximum, in the spherical portion, remember, spherical ends. And part B is the stresses in the direction perpendicular and parallel to the helical welt. This helical welt, perpendicular to it and parallel to it. We have to find sigma W and tau W. Normal stress perpendicular to the weld is normal stress, along the weld is shearing stress in part B. For that we need to find stresses in cylinder. In cylinder we can find sigma 1 and sigma 2. Okay, so let us move. For spherical portion, okay, P is same for both of them, 180 psi. For spherical portion, the thickness is given as T by 5 by 16 inches, which becomes 0.3125 inch. Radius, this R is always inner radius, remember. So outer radius is given, outer diameter is 30 inches, so outer radius is 15 inches. 15 minus thickness, R outer minus thickness is inner radius, or R. So it is 14.688 inches. By putting the values in this expression, sigma 1 and sigma 2 both are same, it becomes 4230 psi. Okay, now we can draw a Mohr circle for the thin wall spherical vessels. So for sphere, sigma 1 and sigma 2 are same, so you will show a dark dot here. It is in plane circle, and then there is a dotted circle which denotes out of the plane circle. Tau maximum is radius of the outer circle. They have not asked us to find tau maximum in plane or out of the plane. They have just simply asked to find tau maximum shearing stress. So maximum shearing stress is radius of the outer circle. In this case it is out of the plane. The in plane in this case is 0. So tau maximum is radius of the outer circle, which is simply sigma 1 by 2 or sigma 2 by 2, whichever you take. So 4230 divided by 2, it becomes tau maximum. In part B, we were asked to find sigma W and tau W. For that we need sigma 1 and sigma 2 initially. We will find sigma 1 and sigma 2 in cylindrical portion. Okay, P is again same. Thickness of the cylindrical portion is 3/8 inches. Internal radius is external radius minus thickness of the cylinder. So it is 14.625. It is different for cylinder and sphere in this case, remember, because thicknesses are different. Okay, first we find hoop and longitudinal stresses, sigma 1 and sigma 2. We know the expressions PR over T and PR over 2T. Or sigma 2 can be half of sigma 1 as well. So simply we have found it. We can draw a Mohr circle. Sigma 1 and sigma 2 both are principal stresses. So we can draw a Mohr circle from two principal stresses. Here it is. Point A denotes sigma 1 and point B denotes sigma 2. We know the numerical values, so we can draw a circle between 2 points. Okay, the average stress is half of sigma 1 and sigma 2, and radius of this circle is sigma 1 minus sigma 2 divided by 2. Okay, so we know both radius and average stresses now. What we have to do, it is very important. Now let us move to the given diagram now. Here we have to find sigma W and tau W. This sigma W, we have to find its angle with direction 1 or direction 2, sigma 1 or sigma 2, longitudinal direction or hoop direction. So let me draw it very clearly here. Sigma W, it is at an angle of, this is direction 2, at an angle of 25 degree, same angle as this one, with the direction 2, with the longitudinal direction actually, 25 degree counterclockwise. So sigma W is at a 25 degree counterclockwise direction with direction 2, with the longitudinal direction. Here is longitudinal normal stress, sigma 2, this one. So drawing a line at 25 degree, in Mohr circle it will be 50 degree, 2 theta, 25 double of 25 is 50. You will draw a line here, cx dash. So the coordinates of this line are sigma W minus tau W. We will remove the minus sign after calculating the stresses. Okay, sigma W, tau W. So we can find it here by making it a triangle. We know this angle. We have to find coordinates of this. This point has the coordinates of sigma W and 0. So let us move and find it. Here sigma 1 and sigma 2 were given. If we rotate it, we can find sigma W and tau W. Here sigma W is perpendicular to the weld and tau W is parallel. From this triangle, from this diagram, sigma W is equal to sigma average minus r cos 50. We make it a triangle and call it point K, for example. So sigma W is equal to OK. It is OC minus CK. OC is sigma average and CK in this triangle, it is R. OC is average, CK is R cosine of 50 degree. R is radius, already known to us. In the previous slide we have calculated radius. Okay, sigma W can be calculated from here. Tau W is simply kx dash, perpendicular of this triangle, which is R sine of 50 degree. Angle is 50 degree. So by putting all the values, we can find sigma W and tau W here. Normal stress or stress perpendicular to the weld and stress parallel to the weld. This was asked in the problem. Okay, next is a problem from exercise 755. Up till now, we have finished the theoretical portion of this chapter. We have covered transformation of stresses using derived formulas, principal stresses, maximum shear stress, principal plane, maximum shear plane, using derived formulas, and then using Mohr circle. We have discussed the Mohr circle in details. 2-dimensional Mohr circle, then 3-dimensional Mohr circle for state of plane stress only, and then we have discussed failure theories, yielding theories for ductile materials, and fracture theories for brittle materials, and then we have discussed thin wall pressure vessels, cylindrical vessels, and spherical vessels. We have solved some example problems on each of the topic. I hope it is clear to all of you. If there is any problem, if there is any question, you can send me an email and I will try to clarify your queries and your misunderstandings. After this, there are some exercise problems which I have chosen to be discussed: 755, 766, 785, 786, 795, 700, 726. So this is an interesting one. I will tell you why I have chosen this problem. So I will discuss these problems in a separate lecture. I hope the theoretical portion, the theory portion of the lecture, including the example problems, are fine for you. If there is any problem, if there is any point to discuss, you can email me and I will try to answer you. I hope everything is clear. Thank you very much.